Hello. Well. All right. So while Vedat is finishing to clean the board, I will just recap what I did yesterday. So yesterday I told you about one particular feature of SLE6, which is called the locality property. And the locality property tells you that if you look at SLE6 in two different domains, but if the local shape of the boundary at the starting point is the same, you don't notice that they live in different domains until you touch a point where the domains are actually different. So if I want to start on the left because it's more proper. So if this is the domain, one statement was that, so say in the upper half plane, if you take the upper half plane and you take SLE6 from 0 in H, and you pick A a hull, then the behavior of the curve up to the first heating time of A was the same as the behavior of the curve in the complement of A until the first time when you touch A like this. So this was very clear for percolation, because percolation at the discrete level satisfies this locality property. It only depends on the local values of the spins, and they are independent of everything else. So percolation implies this property, and this implies that kappa is equal to 6. So that was the main content of the course yesterday, to justify that kappa equals 6 was special in terms of, as one particular value of kappa where something macroscopic like this happens, and it allows us to identify SLE6 as the only possible limit for percolation. And then in the very end, and I will come back to it, I started to speak about the self-avoiding walk. So now I gave you two introductions about the self-avoiding walk, one on the first lecture in the finite domain, and yesterday in infinite domains. And the key idea of these was to state the restriction property. So I want to come back to the initial introduction of self-avoiding walk I did. So here is a domain. This is a simply connected domain with a smooth boundary, as usual. And you take 2 points A and B on the boundary. And then you fix a parameter x, positive. And you look at the set. So the set of walks is not called omega, obviously. It's called, I don't know, W. W is the set of self-avoiding paths from A to B in omega intersection with, say, delta z squared. So you take the lattice z squared. Maybe taking the hexagonal lattice is better. You will see why if you come next week to the invited lecture of Hugo during the course of Gordon State. He will tell you everything about the self-avoiding walk in the hexagonal lattice. But for now, let me draw it on delta z squared. And so on this big W, they are all finite paths. You put a measure, mu x, such that mu x of a given walk is, there is a normalizing factor which makes it a probability measure, times x to the power of the length of omega. So this is the length of omega, just the number of steps. So typically you will have walks like this, which cross the domain, and you want to know something about the asymptotic behavior of that. So this is something I already told you in the beginning. If you look at the cardinality of omega as a function of delta, so the size of this omega, which is depending on delta, so this, well, this is not really what I want to say. Okay, the thing is, if you look at the number of self-avoiding walks of length n, this goes geometrically, and the number of self-avoiding paths of length n, this behaves like some constant to the power n. mu to the n, where mu is called the connectivity constant of the lattice. So in the case of Z2, it's not known. In the case of the hexagonal lattice, it's square root of 2 plus square root of 2. And that tells you that somehow, if you want this to look like a uniform path of a given length, you need to pick the parameter in such a way that the sum over this is of order 1. So you want to penalize the longer walks by having x finite, and the shorter walks will be penalized because there are not as many. So it tells you that it's reasonable to take x critical equal to 1 over mu. And this makes you predict that if x is less than x critical, then what you do is, if you look at the measure, you will concentrate your measure on shorter paths. And this measure, so the path under mu x, will converge to something straight, to a straight line, as delta goes to 0. So if it's more and more difficult to have a long path, it makes the direct path most likely, and it just goes straight. And if x is bigger than xc, then you want the path to be as long as possible, and you end up with something which is space-filling. So this is something I already said during the first week, so I'm just reminding you of the definition of x critical. But there is something else that is satisfied by this measure here, this measure mu x, which sounds a little bit similar to this statement here. So the question is, take a domain omega, and now take a hull here. So A is an obstacle. It's something that touches the boundary. The complement of A is simply connected. It still contains A and B on the boundary, so A is really something like that. It's an obstacle, but it's possible to go around the obstacle. And the question is, so what is the behavior of a walk chosen according to this measure if you condition it to avoid A? So what is mu x of something conditional on the event that omega intersect with A is empty? Well, it's still a measure on a finite set, so you can compute the probability. So mu x of a given omega, given that you avoid A. Well, first of all, omega needs to actually avoid A. So that will be equal to indicate a function that omega intersect A is empty. And then there will be the measure of omega itself, which is still x to the length of omega, divided by z. And then there will be the probability of avoiding A in the conditioning. So that will give you a factor 1 over mu x of avoiding A. Okay, so that's just basic probability. It's the computation of a conditional probability. Okay, now what would happen if you constructed mu inside the complement of A? So if you look at mu x in omega minus A of a given path, notice that here I can choose omega which does not intersect A, and that means that omega is a path from A to B in omega minus A. I can compute the mass of omega in this domain. So the definition is the same. The mass of a path is 1 over z times x to the length. So of course, the partition function here depends on, or is the partition function on omega, it depends on x. And here it's on omega minus A, depends on x. And then there is a factor in x to the length of omega. That's still the same. And so if you stare at these two formulas, you will notice that the only dependence in omega, assuming that omega is admissible in both cases, is the same on both sides. is this x to the power omega here. The rest is just normalizing constants. And so because these two have to sum to 1, what you get is that the sum of our, is that this normalizing factor here is exactly equal to this normalizing factor here. And then once normalized, it tells you that mu x in omega conditions that omega intersect A is empty, that's the same as mu x in omega minus A. So this is a trivial statement. It's just a basic fact about uniform measures or about measures such that the weight of a path depends only on the features of this path and not on where it lives. So it is satisfied for every value of x. It's satisfied in many cases. So it's also satisfied in the infinite self-avoiding walk I mentioned yesterday. So the way you define the self-avoiding walk in the half plane, then what you get satisfies this restriction property. So I will restate. This is called the restriction property. Okay, and so as you can notice, it does not depend on the choice of x. So this phase transition is not making the restriction property appear. It's making something else appear. It's making something appear at x critical. Okay, so now you go to see your favorite physicist and you tell him that you have this one parameter family of measures and you ask him what they do in the scaling limit. And he will tell you that, okay, there is a renormalization group theory behind it, and if you start away from x critical, you will become essentially deterministic or something complicated. But if you start at x critical, you expect to have some scale invariance. So at x critical, you can predict that there will be scale invariance, and there will be some universality which will predict as well that somehow you expect conformal invariance. Conformal invariance as delta goes to 0. So this is something that one can expect. Nobody can prove that actually there is conformal invariance for the scaling limit of the self-avoiding walk, either this definition or the definition in the half plane I explained yesterday. But nevertheless, it's very well tested numerically, and there are some good reasons that you should expect it. So if you've been following my course from the start, you know that if you have a simple curve and it has conformal invariance and it has the domain Markov property, you expect it to be an SLE. So what about the domain Markov property? Well, once again, the domain Markov property is very easy to check in this definition. If you condition the path by its first 12 steps, so this is the location of the first 12 steps, what is the probability that the rest of the curve is something? Well, you do the same computation here, except instead of conditioning to avoid A, you're conditioning to start by the first 12 steps of omega. But the computation is the same. It depends only on the length of what remains. So what you get is that the distribution of the future is the same as the initial measure in the complement of the initial segment. So that was clear in the case of the exploration path of percolation. It's clear again in the case of the self-avoiding walk with this definition. So you do have the domain Markov property. So you expect that the limit should be an SLE. So it should be an SLE kappa for some kappa. And the question is which kappa? And here, what we are going to do is to focus on the restriction property and try to find some value of kappa for which SLE does have this restriction property. And if we can find such a kappa, then we will know, and if it's unique, then we will know that this is the unique possible scaling limit for the self-avoiding walk. And we'll have a nice conjecture. We have no proof, of course, because Nobody can prove that there's a scaling limit, but we have an explicit conjecture that the scaling limit has to be this. So this is the question. For which value of kappa do you expect the restriction property for SLE? Okay. So, well, let's start. I will remind you of the computation I did yesterday because the start of the computation is essentially the same. Here we wanted to compare SLE up to hitting A and SLE in the complement of A. Now we want to compare SLE not hitting A with SLE in the complement of A, but the frame is the same. We want to compare SLE in H and SLE in H minus A. So I will redo the pictures I did yesterday, just to put them back in your mind somehow. So here is the upper half plane. Here is A. And here is the curve gamma. So this is 0. I'm still writing it as a simple curve, and now it will be a simple curve because it's the limit of a self-avoiding walk which wants to be more like a simple curve. So remember there was the map GT that removes gamma up to time t, like this. So it maps the complement of gamma t back to the upper half plane. This is the image of gamma t. This is beta t, which is the driving function of the initial SLE. And it maps the obstacle A to something, which is GT of A. Okay, and then we have another family of maps. First, we want to remove A by a conformal map. So we have this map here, which is phi A, which maps the complement of A back to the upper half plane with the same normalization at infinity. So this is what becomes of A. And now it maps the curve somewhere here. And this is something I called gamma tilde t. Maybe I didn't call it gamma tilde t, but it will fit with the rest of the notation. And then there was the second copy of a Lovener chain, which was G tilde, removing the image of gamma by the map phi A. So it finally removes everything here. There's something like this. This is the image of A. Okay? And the last part of the picture is the map that removes GT of A, and this was what I call H sub t here. And because of uniqueness and because of the normalization, what we had was that this and this was equal to this and this. So this was the same as H0. Okay, so that was the picture I was looking at yesterday. And I started to compute a few things, enough to get some particular feature at kappa equal to 6. So let me remind you what I did as a computation. So here it is. First of all, I defined the time parameter A of t, which was the time parameter of the composition here. So that was just A of A plus A of k tilde t. Okay, and what I told you is that the time derivative of this, A prime of t, was given by looking at the image of something macroscopic on top here. This it has size epsilon. Then you map it by H. H behaves like a scaling around the point beta t. This was, of course, beta tilde t here. And so it scales by H prime, and because of Brownian scaling, what we had is that A prime of t was equal to H t prime of beta t squared. So that was the first estimate. The second estimate was something about the driving function here. We applied Ito's formula to get that d of beta tilde t was given by, so you write beta tilde is ht of beta t, and you apply Ito's formula, and what you get is that this is ht prime of beta t d beta t plus kappa minus 6 over 2 times ht double prime of beta t dt. So this was the driving function of the new process, which is the conformal image of the initial process by phi a. Okay? Then what you notice here is that if kappa is equal to 6, if kappa is equal to 6, then this is a martingale, because the drift term disappears. And so you are back into an SLE. You recognize that this is the square root of a prime. So you recognize that it's exactly fitting the time change that you would have if you wanted to parameterize the curve by a Löwner chain. And what you get is that gamma tilde is an SLE6 again. So that's more or less the proof I explained yesterday. And I just wanted to put it back in your mind because the thing we are going to do now is essentially very similar. Okay, so apparently I keep saying okay all the time. Question is there another value of kappa for which something magical like this will occur? So one thing we can look at is this ht prime of beta t. Here it appears as a time change, but essentially it disappears because we recognize that here is the square root of the time change. So whatever it is, it's not really relevant. Just what is important here is that the drift term disappears. But now what we want to do is to look at it more precisely, at ht prime of beta t. So it's something I said already yesterday. If you look at ht in the neighborhood of beta t, well, the boundary of the domain here is flat because we just removed everything up to time t. So ht is conformal in a little disk like this around beta t. And the boundary is flat, so you can do Schwarz reflection. So you can apply Schwarz reflection, which means that you define it across the real line by letting ht of z bar to be equal to ht of z bar. And that makes it holomorphic in a disk centered at beta t. And in particular, you can derive it, we can differentiate in z as many times as we want around beta t. And it will be smooth, and it will have as many derivatives as we want. And besides, so if you look at what h does, it maps the upper half plane around beta t to the upper half plane above beta tilde. And the restriction to the real line is real. So that means that all the derivatives are real, and ht prime is positive. So essentially, we are doing real analysis, but the smoothness is justified by the fact that everything extends to a holomorphic map in the neighborhood of beta. Okay, one formula I wrote yesterday about ht prime of beta t was this. We had that dt ht of z, dt of ht of z. What I wrote was that this was equal to 2 ht prime of beta t squared over ht of z minus beta t minus 2ht prime of beta t of z divided by z minus beta t. And this is a beta t tilde. So I wrote this formula, and this formula comes from the fact that this composed with this is equal to this composed with this. So you can write ht as a composition of first gt minus 1, then h0, then gt tilde. And you know the derivative of each of the terms. So what you get is a composition of terms. And you get this. OK, what happens is, so I'm just doing a computation, and I will tell you afterwards that it was reasonable to do. What happens if you look at, so we want to know about the derivative of ht. So what happens if you differentiate this in z? So dz of this. Well, you just do the computation, and it's a chain rule thing. What you get is that dt of ht prime of z is, well, whatever comes out in the computation, and I will just write it down for you here, because if I try to do it live, I will get it wrong. So minus 2ht prime of beta t squared ht prime of z over ht of z minus beta t tilde squared. So this is what happens when you differentiate this in z, when you differentiate this h in z. And then there is a plus 2ht prime of z over z minus beta t squared, which is what happens if you differentiate this in z. And then there is a term which happens when you differentiate the ht prime on top in z. And this term that you get is exactly minus 2 ht double prime of z divided by z minus double t. OK, and there is no derivative here because this is not z. So this is all you get. There are 3 occurrences of z in the formula, and you get 3 terms. So this is what you get. And now we want to know something about the behavior at beta t. So we want to let z go to beta t. And OK, this is a beta, this is not a w. As z goes to beta t, all the denominators go to 0, because ht of z goes to ht of beta t, which is beta t tilde. This goes to 0, this goes to 0. So you need to hope that the first order terms will vanish, and the first term that doesn't vanish is order 1. So what you do is you expand on top everything that depends on z around beta t. And you know it's possible because you know that h is smooth in the neighborhood of beta t. So you can expand in series. You know it will converge with positive radius of convergence. So as z goes to beta t, it's valid to do that. So you just expand this ht prime here, the ht double prime here around beta t. And you figure out what remains. And what remains is this. The dt ht at point beta t is equal to, so ht double prime of beta t squared over 2 ht prime of beta t minus 4/3 of the third derivative of ht at beta t. So this is what you get. So it's natural to do that because, so that's an ht prime, of course. It's natural to do that because we want to know something about ht prime as a function of t. So we want to know about the time derivative. It's a natural way to do it. The details of the computations themselves are very boring. You just need to expand, and it's calculus. So you just do it, and hopefully you get the same answer here. The relevant parameter here, of course, is this 4/3 here. The rest is very predictable. But this 4/3 here will be critical in what follows. So once we have this, then, well, what we want to do is study ht prime as a process, ht prime of beta t. We know the time derivative. So this, as a process, will be given by Ito's formula, as we did yesterday. So yesterday we were focusing on just the driving function. Here, instead of focusing on the driving function, we look at some observable, which is ht prime at beta t. But the general framework of the proof is the same. We write a process, we write Ito's formula, we see what happens, and we will say that there will be one value of kappa for which something will occur that will make us say something intelligent about the process at this particular value of kappa. So maybe I should keep the restriction property here. So we will apply Ito's formula to the process. And the process is just the ht prime of beta t. So here we go. It's the same Ito's formula as yesterday, except instead of looking at ht of beta t, we look at ht prime of beta t. So what you get is that the variation of ht prime of beta t, what will it be? It will contain three terms. There will be the time derivative of ht, which is what we just computed, and then there will be the Ito term depending on the behavior of beta t here. So the first one is complicated. There are these two terms over there, and then so what you get is four terms. And what you get in the end is that this is ht double prime of beta t d beta t. So that's the first term in the Ito's formula, plus something big in terms of dt, which collects all the other terms. So there will be this ht double prime of beta t over 2 ht prime of beta t. So this h double prime is squared. That's the first term over there. And then there will be something like plus 3 kappa minus 8 over 6 times the third derivative of h at beta t dt. So here you will recognize that there is this 4/3 which comes from there. And there will be a kappa over 2 which comes from Ito's formula here with the second derivative of ht prime, which is h third derivative here. So this is what you get. And of course, the first 2 or 3 times you don't get this, you get different factors because you get the computation wrong. But this is the right answer to the computation. So this is not yet something very simple because we don't really know what ht double prime is. We don't really know what the third derivative is. But it already tells us that something will occur. So something will occur if we choose kappa such that 3 kappa minus 8 over 6 is equal to 0, meaning that kappa will be equal to 8/3. So this time kappa equal to 8/3 will be the special value of kappa that will make things work. And then you will notice that this factor here vanishes. So we are not having a martingale yet because there is still this factor in front. So what you can do, well, if you are into stochastic calculus, you will know exactly what to do. If you want to cancel this term in dt, well, instead of looking at ht prime, you look at ht prime to some positive power. So you look at d of ht prime of beta t to some power alpha. So this is the alpha power of this, so you can write Ito's formula. The term in beta t will be multiplied by some alpha, and you will get 2 terms in dt, this one and the Ito term coming from the alpha derivative power here. And then you will be able to cancel it by choosing alpha approximately. And what you get is that if you take alpha equal to 5/8, and this is just what you need to cancel everything, then the contribution in dt will vanish. So this one is cancelled by choosing kappa, and this one is cancelled by raising everything to the power of 5/8. And what you get in the end is exactly this. You get 5 ht double prime of beta t squared divided by 8 ht prime of beta t to the power 3/8 d beta t. Okay, so that was just a long, boring computation. If you fell asleep during the computation, this is when you need to wake up again. This is the byproduct that we get from all this computation, and now you can forget about everything I told you. You can forget about why we did this computation. You can just look at the formula here. This tells us that if you take SLE for kappa equal to 8/3, and you look at ht prime of beta t to the power 5/8, then this is a local martingale. So ht prime of beta t to the power 5/8 is a martingale. It's a local martingale, but it's a martingale because it's easy to see from complex analysis that it's bounded by 1. So you get exactly a martingale. So, okay, then you might say that that was some computation we were allowed to do. What does it have to do with the restriction property? So now we'll erase the restriction property from the board, and it will come out again from the computation. So here's something to test your reflex. If I tell you that something is a martingale, and I want to look at the process in the complement of A, I want to test that the heating time of A is infinite, because that will tell us that I don't intersect A. So you have a martingale and you have a stopping time. There's a unique thing you can do with this. You just want to apply the stopping theorem. So we did all the thinking when setting up the picture. Now we have a martingale, we have a stopping time, so we just apply the stopping theorem and see what happens. So let tau be the heating time of A, or infinity if you don't touch A. And apply the stopping theorem to the martingale, which is ht prime of beta t to the power here, 5/8, to the stopping time. So tau is inf of t such that gamma t is in A. And the probability that k avoids A is the probability that tau is equal to plus infinity. So I choose tau to be infinite if this does not occur. So I want to apply the stopping theorem to this martingale. I want to call this, well, it's short enough. So the stopping theorem tells me that if I look at this for t equal to tau, I will get the same thing in expectation as what I have at t equal to 0. So at time 0, remember h t for t equal to 0 is phi a. If the maplet removes a, and beta t is equal to 0, so this ht prime of beta t is just the derivative of phi a at 0. So it tells me phi a prime of 0 to the power of 5/8 is, say, the limit as t goes to tau, well, of the expectation of this. So if I want to extract something out of this, I want to look at the behavior of this term here when t goes to tau. So there are two cases. The case where tau is finite, and the case where tau is infinite. So I'm putting them here, but I will draw pictures on the next column here. So first of all, what happens if tau is infinite? If tau is infinite, it means that A is somewhere here, and the curve avoids A. And it goes to infinity without touching A. So what happens for large t? So I stop this at large t. So t is very, very big. ht prime will be read here. So the first thing I want to do is apply gt. So what gt does is it opens this, and it will push A very far away, just because you need to fit the image of this half here somewhere. So if you map the picture by gt, what you get is something like this. So this is the image of gamma. This is beta t. And this is gt of A. So maybe this is a bit longer, but the key is that the image of A is pushed away by the flow of the process, just because the size of this is very big with respect to the size of A. So now if you look at what ht does, ht removes gt of A from the picture, but it's normalized in such a way that it's very close to identity if you are away from wherever the thing occurs. If you remove gt of A from the picture, you will not notice if you are sitting at beta t. You are removing something very small, very far away, and this will tell you that ht will look very much like identity around beta t. So if tau is infinite, what you get is that ht prime of beta t goes to 1, which is the derivative of the identity around beta t. Okay, maybe I should put them in the same order. So if tau is infinite, ht prime of beta t goes to 1. Now, what happens if tau is finite? If tau is finite, you start with the same A, start here, and there is a finite time at which you touch A. And I will look at t, which is very much, well, very close to tau, but a little bit smaller. So t is tau minus epsilon. So I almost touch A at time t. And then if I wait a little bit more, I will touch it. So again, I want to say something about the map that sits here. So I want to apply gt. So again, gt will open this curve up and spread it on the real line. So what you get is something, for the moment, is very similar. This is the image of the curve. This is not a loop in the curve because A is just some test set, but G does not see the set A. So the two halves are roughly the same size. So beta t is somewhere here. But now if you look at A almost closes a loop between some point on the boundary, which is here. I will use color here. Between some point of the boundary, which is the image of this by gt, and the image of this, which is here. So you know that the image of A by gt will contain the image of this curve here. And this curve will be mapped to something that does something like that. So in the end, the image of A by the conformal map will probably look like this. So this is gt of A. So because A was almost closing a loop when added to the curve, once you remove the curve, there is still something that almost creates a loop, and that has to be the image of A by GT. So this is what you have. So now what HT does is that it removes everything here from the picture and maps everything back to H, like this. And you want to know the behavior of H around beta t. So what you have is, in particular, if you remove this, well, you will map the whole complement to H, but it's still a conformal map, so it has to preserve the harmonic measure, or the size seen conformally from infinity. So now if you focus on what's inside here, this is very small in terms of harmonic measure. If you start a button motion from far away, it's very unlikely to enter here and touch inside. So if you map the picture by HT, this will be mapped to something very small. But the way you map this tells you something about the derivative of H around this. And so because this is large in diameter here but small in harmonic measure, it tells you that the derivative of H here has to be very small. And then as epsilon goes to 0, the diameter of this guy does not go to 0, because tau is nothing special in terms of G. You just arrive somewhere in space. So this will converge. But the harmonic measure will go to 0 because the opening here will vanish. And so what you get is really that the derivative of H at beta t will go to 0. So this is what you get. So if you plug this into the stopping theorem, you will see that there are two cases. Either you survive or you don't. And if you survive, this goes to 1. And if you don't survive, this goes to 0. So as t goes to tau, the only thing that remains is the probability that tau is infinite, which is exactly the probability that gamma avoids A. So now I can remove the picture and give you the conclusion of this. So the conclusion is that if you look at SLE for kappa equal to 8/3, then the probability that gamma avoids A is just given in terms of the derivative of phi A at 0. So what you get is this. For every hull A, if phi A is the map that removes A from the picture, then the probability to avoid it is equal to phi A prime of 0 to the power 5/8. So here's the theorem that we get. So for every hull A, the probability that SLE 8/3 avoids A is equal to phi A prime of 0 to the power 5/8. So this is what we get from all these considerations here. There's a very simple formula telling you with which probability you avoid a set with SLE 8/3. So of course none of this would remain if kappa is not equal to 8/3, because it was all based on the fact that this was a local martingale. So there is no simple formula like this in a general case to compute the probability that you avoid A. And of course there's the converse. The probability that you do touch A is 1 minus this. So if you fix A, which is very small on the boundary, you can estimate, say, the probability that you touch something very small on the boundary and compute the boundary exponent. So that will give you something that is in the same flavor as what you did in the exercise session yesterday, So you computed yesterday the probability to touch something very small in the bulk. If you want to touch something very small on the boundary, at least in the case kappa equal to 8/3, you can do like this. And it's much simpler than what you did yesterday. All right, what does it have to do with the restriction property? So now, I want to look at SLE 8/3 conditioned to avoid A. And I want to know if this is the same as SLE 8/3 in the complement of A. So to test that I have SLE, I want to compute the probability that I avoid something else. So A is a hull, and it's fixed. And I want to compare SLE 8/3 in H minus A compared to SLE 8/3 conditioned that gamma intersect A is empty. So I have two distributions on curves in the complement of A, and I want to know if they are the same. So the way to do that is when I fix B a hull. So B will be my test hull, it will change, and I want to show that for every B, the probability for this guy, that SLE 8/3 H minus A avoids B. If I can prove that this is always equal to the probability that gamma in H avoids B, conditionally on the fact that it avoids A already, so given that gamma intersect A is empty, if I can prove that these are equal, then I'm done. I know that the curve is the same in distribution because it's enough to know these probabilities to characterize the distribution of a curve. If I know which hulls I avoid, I know the curve completely. So how do I compute these two terms? Well, one is very easy and the other one is very easy as well. So let's start with the second one. So the second one tells me that I need to compute a conditional probability. And that's just a ratio of probabilities. It's the probability that I avoid both A and B divided by the probability that I avoid A. And all I did for the last half an hour was to tell you how to compute the probability that I avoid a given set. So I know how to compute this conditional probability. It's just a ratio of derivatives of conformal maps. So I can do the computation explicitly. So there will be A and B, which are two hulls in the upper half plane. And there will be one particular conformal map, which will be phi A union B, which removes both of them. So there's one little technical problem, which is that I want to start everything at 0. I want to launch SLE at 0. And the maps phi that I have, they are normalized at infinity to be z plus something over z. But they don't fix the origin. So just a notation. If C is the hull, I will denote by big psi of z, psi c of z. This is the conformal map that removes C from the picture, that maps H minus C back to H. So H minus C to H. And it's normalized in a different way. It's normalized by saying that psi c of z is z plus big O of 1 at infinity. So there's one less term that you know. You don't know that the constant term is 0. You just know that it's bounded. So you need one more real parameter. And this is normalized to have psi c of 0 equal to 0. So just to fix things, psi c of z is nothing else than phi c of z, normalized as before, minus psi c of 0. So it's just phi as usual, but it's shifted so that 0 is fixed. So because of this, well, the derivative at 0 is the same. So phi c prime of 0 to the power 5 over 8 is the same as psi c prime of 0 to the power 5 over 8. So this is just a play on notation just to make the things a little bit easier. So I want to prove that for every b, this, which is 1, is equal to this, which is 2. So as I told you when I was erasing the board, we can start by computing 2. So 2 is the probability that gamma avoids both A and B, so that gamma intersection A union B is empty, divided by the probability that gamma avoids A, which is the condition. Okay, probability to avoid A union B, that's just psi A union B prime of 0. So it's psi A union B prime of 0 to the power 5 over 8. That's what we have from SLE computations. And the probability to avoid A is psi A prime of 0 to the power 5 over 8. So this is the computation for 2. And let's leave it like that for the moment and turn to the study of 1. So 1 is the probability that gamma defined in H minus A avoids B. If you remember what I told you on Monday this week, the way you define SLE in H minus A is you define SLE in H and you map it conformally to H minus A. And we have a map that maps H to H minus A. It's just a reciprocal of psi sub A. So 2, so 1 here is just the probability that SLE in H minus A, which is just psi A minus 1 of gamma, so this is SLE in H minus A. This has to avoid B. So this intersect B is equal to the empty set. This is just a way of rewriting the definition of 1 by using the definition of SLE in H minus A. Okay? So now what does it mean that psi A minus 1 of gamma avoids B? I can map that by psi A. That's the probability that gamma avoids psi A of B. That's equivalent. I just relate the two pictures by psi A. And so this is the probability that SLE avoids something. So this is given as psi prime to some power at 0. It's some psi, the psi that removes psi A of B. Prime at 0 to the power 5 over 8. So maybe here a picture would be a good idea. I have A, I have B, I have psi A that removes A, and it maps B to psi A of B. So psi A is here. It removes A. It changes B into psi A of B. Then we have psi A, that's the same psi A. We have psi A union B, which removes everything. So it does something like this. This is psi A union B. And 0, let's put 0 on the picture, assume it's in between. It doesn't really matter where it is. It is fixed by everybody. And then there is this map here. This map removes psi A of B. So this map is just psi sub psi A of B. It's this map here. So this is psi sub psi A of B. So because of the normalization that I chose, everything is unique, everything fixes 0. So what we have is that this is the composition of this and this. So psi A union B is nothing but psi A of B composed with psi A. This is from uniqueness of the conformal map that removes a set. And now because they all fix 0, what I can do is I differentiate this in Z at 0. And I get that the derivative here, so psi A union B prime of 0, this is just a product. So it's psi prime of psi A of B prime of 0 times psi prime A of 0. It's just saying that the derivative at 0 of this is the product of this and this. So now if you check, it tells you that this derivative times this derivative is equal to this derivative. So it tells you that this is equal to this. So this is equal to, so this was 1, and 1 is equal to 2. So this is what you get. If you can write the probability to avoid the set in terms of a derivative at 0, then automatically you can compute conditional probabilities very easily. And what you get is that this probability is equal to this probability, meaning that SLE says in H minus A is the same as SLE says in H condition to avoid A. So what you get from this is that the corollary of this computation is that SLE thirds has the restriction property. And in fact, it's not very difficult, and this is what I will tell you just now, to show that SLE thirds is the unique SLE having the restriction property. So SLE thirds is the unique possible scaling limit of self-avoiding walk in the upper half plane. Okay, everything is okay so far? Yes?
The argument that you have just presented doesn't make any relation with third.
No, except, no. It only uses the fact that this is true. So the statement that A3 is the unique one is a statement that SLE A3 is the unique one for which you can write this probability as phi prime to some power. But you're right, this argument to the right of this line is nothing specific to SLE. It's just unique using this estimate. And this is exactly what I'm going to tell you right now. So maybe I should write this formally. The argument I just explained here tells you that if you have any random subset of H for which you can compute the probability of avoiding a hull, and for which this avoiding probability is given in terms of the derivative of phi A at 0, then automatically this satisfies the restriction property. So this is what you can extract from what I just told you. So I will just write it, and then we will look at whether it's an equivalence. And it turns out that it will essentially be an equivalence. So what we have is this. I'll give you a definition of what a restriction measure is. And then I will tell you that something is a restriction measure. So definition. So a restriction measure is a measure on, let's say, closed subsets of H bar, which I will denote by K. So not K like compact, but K like closed. It's a restriction measure is like a compact, a closed set which is random, but the distribution is supposed to satisfy the restriction property, so such that the law of K, given that K avoids A, is the same as the law of psi A minus 1 of K. So that's just saying that K condition to avoid a set is the same as K in the complement of this set, but you define it by conformal map already. So this is the definition of a restriction measure. If you want to condition K to avoid A, you just push H to H minus A. You push K by this, and you get the distribution that you wanted. So all I proved for now is that SLE 8/3 is a restriction measure. So SLE 8/3 is a restriction measure. This is because it has a restriction property. This is what I just proved. And in fact, I proved something a little bit stronger. If K, which is a random closed subset of H bar, is such that the probability that K avoids A is equal to psi prime A of 0 to some power alpha for some positive alpha, then K is a restriction measure, or the law of K is a restriction measure. So you will have the restriction property as soon as the probability to avoid the set is given by a derivative at 0 of a conformal map that removes the set. So I still have something like 20 minutes, I think. So what I will tell you is something about the inverse statement. What will be true eventually is that any restriction measure satisfies this, that the probability that it avoids a set is given by phi prime A of 0 to some power. So the aim is this, and the proof is almost already on the board because it's essentially the same. If you take any restriction measure, then there will be an alpha such that this is true. Just while I'm erasing the board, notice that technically so far, knowing that this probability is like this does not characterize the distribution of K completely. So I need a technical assumption which will tell me that, in fact, I will not define the restriction measures on closed subsets of H bar. I will define it on particular subsets. I want K to look like this. So I want K to be like this. meaning I want k to touch the axis only at 0. This is not really part of the requirement. It will come out of what I will tell you, but essentially I want k to have no hole. So I want the complement of k to have two connected components, one that touches the real positive axis and one that touches the negative axis. But I forbid k to have holes inside. And the reason is, if I assume this on k, if I assume this topological feature, then the distribution of k is given by the distribution of its two boundaries, on the right and on the left. And this now is characterized by the probability that you avoid hulls that touch the boundary. If you know for every a the probability that you don't touch a, and if you know that k has no hole, then you know everything about the distribution of k. So it's the same kind of trick I used when I spoke about the invariance of Brownian motion under conformal maps. If you want to say something about a compact, it's very complicated. If you want to say something about a compact from which you have filled all the holes, all you need to know is the probability that you avoid something that is attached to the boundary. So I am assuming this of all the restriction measures here. Yes? It's part of the picture. Everything that is satisfied by this picture is an assumption on k. So it has to be connected. It has, or if it's not connected, then the complement is not two connected components like this. But thanks, it has to be connected. Okay, so I told you that if k is such that this is equal to phi prime a of 0 to power alpha, then it's a restriction measure, and it characterizes this restriction measure uniquely. In fact, what is true is the following. If k is a restriction measure, then there is some alpha positive such that for all a, the probability that k avoids a is equal to phi prime a of 0 to the power alpha. So these are the only restriction measures that exist. If you have the restriction property, then the avoiding probability is given by the derivative of at 0 to power alpha. So I just give you an idea of the proof, but the proof is almost already on the board. So it's the same proof as when you say that any additive function has to be linear if it is continuous. What you do is you want to say that you start with a restriction measure. It has this. And you take two sets, A and B, and you want to compute the probability that you avoid A and B. So you don't know yet that it's related to psi A union B, because that's what you want to show. You want to show that alpha exists. But what you know is that it is the probability to avoid B times the probability that you avoid A given that you avoid B. And then you know that given that you avoid B, you are the same as what you are in the complement of B. So you know that the probability to avoid A and B is this product. Is the probability that you avoid A times the probability that you avoid psi A of B. So you know, you don't know that this is phi prime, but you know that the avoiding probability of A union B is this product. So you know that probability to avoid A union B is the probability to avoid A times the probability to avoid psi A of B. And this has to hold for any sets A and B that touch the boundary like this. So now you take this relation and then you shake it a little bit, and it's not difficult to arrive to the fact that this implies that automatically this is a morphism. This is some kind of morphism property. It tells you that if you take more sets, you have to take a product at 0. So the only thing you can do is to look at the derivative at 0. So I leave it as an exercise. It's not something complicated, but it's a bit messy. You need to prove something about continuity. One way is to describe the boundary of A by an SLE or by a Loeffler chain or something like this, and look at the derivative at 0 of the conformal map, and relate that to the derivative of the probability to avoid AT. So it's not complicated, but it's something that you need to do for yourself to convince yourself that it works. But I choose not to do that because the sequel of the story is more interesting than the proof of this result. So this result, I leave it as an exercise. So the question is, now we have this theorem. We know that if K is a restriction measure, then the avoiding probability is given by this formula. And so there is at most a one-parameter family of restriction measures. And the question is, for which alpha does this restriction measure of exponent alpha exist? We know that any restriction measure is one of the alpha restriction measures like this, but we don't know for which alpha you can actually find the distribution on compact sets that satisfies the restriction property and this formula with alpha. So let A be the set of alpha such that the restriction measure of alpha exists. So far, we don't know much about A. We know that it's non-empty because we know that 5/8 is in A. And the restriction measure of exponent 5/8 is SLE for kappa equals to 8 cells. This is all we know for now about the set A. We know it's not empty. So there's something else that we can say, which is essentially trivial about the set A, is that if you have two restriction measures of exponent alpha 1 and alpha 2, it gives you two random sets K1 and K2. What you can look at is the union of K1 and K2. So you take them independent, you take the union, and then the probability that the union avoids A is the same as the probability that's, so you take the union and you fill the holes, of course. The probability that the union avoids A is the probability that both avoid A. And because they are taken to be independent, then this is given by the product of the probabilities. And now the first probability is phi prime of A at 0 to the power alpha 1. The other one is the same to the power alpha 2. And so the product is given by the derivative with power alpha 1 plus alpha 2. So what you get is this. For any alpha 1 and alpha 2 in A, the sum of them is in A. So A is not empty, and in fact, A is already pretty big because it contains infinitely many terms. So this is a remark. If alpha 1 and alpha 2 are in A, then alpha 1 plus alpha 2 is also in A. And that's because if you take a restriction measure of exponent alpha 2, and take the union of an independent restriction measure of exponent alpha 2, this is the same as the restriction measure of exponent alpha 1 plus alpha 2. So we have, in fact, plenty of restriction measures, but they all look the same. They all look like a bunch of SLE thirds independent. Yes? Yeah, that's something I said while I was removing the board. And by this, I mean you take the union and you fill the holes. So the picture is something like this. You have one curve here. You have an independent curve like this. Maybe it does like that. And the way you take the union is you take the union and then you fill everything in order to come back to this assumption. And then what you get is the restriction measure for exponent alpha 1 plus alpha 2. Okay, one natural question, which is going to take me maybe the last 10 minutes, is that there is another restriction measure that you know, but you don't know that you know it yet. So another example is given by simply Brownian motion. In fact, Brownian motion excursion. So what do I mean by that? I will do mostly pictures because that's very graphical. So here is H. And I will pick two parameters, epsilon and r. So epsilon is very small. Epsilon will go to 0, and r will go to plus infinity. So this is the origin. What I'm going to do is I want to define Brownian motion in H, started at 0 and conditioned to go to infinity without touching the boundary. So the way to do that, one way to do that, is I start at I epsilon. This is level I times r plus the real line. I take Brownian motion from I epsilon, and I condition it to reach, so I want to call this line delta r. I condition it to reach this line before it reaches the real line. So to reach delta r before reaching r, which is delta 0. So that's a path that starts here. It looks like a Brownian motion. Locally, it's a Brownian motion with some drift. But I want it to touch height r before it touches height 0. So what you know about Brownian motion in the plane is that it's just two coordinates that are independent Brownian motions. So the x coordinate of this guy is not affected by the conditioning. And if this is zt, zt can be written as xt plus yt. And xt is the just Brownian motion in R. It's not affected, it's just a real valued Brownian motion. And the y coordinate is, again, a real valued Brownian motion from epsilon, conditioned to touch r before it touches 0. So this is Brownian motion condition that r is before 0. So the definition of the Brownian motion excursion in H is the limit of this guy as epsilon goes to 0 and r goes to infinity. So I'm not telling you why it exists, but it's very standard. And if you know a lot of stochastic calculus, you can write it differently. You can write it as this process, where x is Brownian motion and y is just Bessel's 3 process from 0. This is what you get if you condition Brownian motion not to touch 0. But you can take the existence of the thing for granted. You don't need really to know how to construct it to prove anything with it. What you do know is the probability of the events by which you condition here. The probability that a Brownian motion started at epsilon reaches r before it reaches 0. This is again given by the stopping theorem. Brownian motion is a martingale. You start at epsilon. You look at the expectation when you touch either r or 0. So that's just r times the probability that you touch r. And what you get is that r times the probability to touch r before 0 is equal to epsilon. So the probability to touch r before 0 is just equal to epsilon over r. So this is known as the Gambler's rule estimate. It's something very classical. But it tells you the probability of the event by which you condition. It's just equal to epsilon over r. And this will be the only estimate we need when we want to prove that this is a restriction measure. So this is something I will write somewhere. The probability of the conditioning here, so the probability starting from I epsilon of reaching delta r before delta 0 is epsilon over r. Okay, so we are assuming that this converges as epsilon goes to 0 and r goes to infinity. So we get this subset of the plane. And if we fill the holes, this is one of these measures. It will look like this. It touches the axis only at 0 because it's not allowed to touch anywhere else. And what we want to know is why this would be a restriction measure. So what we will prove is directly something like this. So let's do that. I fix A. A is here. I'm assuming that A is at scale 1. So epsilon is much smaller than the scale of A, and r is much bigger than the scale of A. So this is 0, this is I epsilon, and this is delta r. So what is the probability for Bonan motion starting here that I avoid A and I touch delta r before I touch delta 0? So probability that delta r before delta 0 and z avoids A. Because then I will condition by this event. I will let epsilon go to 0 and r go to infinity. And this will tell me the probability that the excursion avoids A. And if I can compute this, then I can check that it's phi A prime of 0 to the power alpha for some alpha. And this will tell me that it's a restriction measure. So if this is what I want to show, somehow it tells me that phi A is something relevant to look at, or psi A. So let's map the picture by psi A and see what happens. So it removes A. Of course, that's the definition of psi A. So this is what remains of. So this is psi A of the boundary of A. 0 is fixed. And epsilon is very small. Epsilon is much smaller than A and much smaller than the distance between 0 and A. I'm allowed to do that because epsilon will go to 0 eventually. So I epsilon is mapped to something that is like I epsilon times psi prime A of 0. And psi prime A of 0 is positive, and we know that psi A is smooth around 0 by the Schwarz reflection as before. What does it do with delta r? So this is psi A of delta r. Well, now the normalization of psi is given by psi A of z is z plus z minus phi A of 0 plus big O of 1 over z. That's the expansion at infinity. We know the first term is z. We know the shift term is given by phi A of 0. That's the way we shift everything back to 0. But this is a real value. And then there's big O of 1 over z. So if r is very large in front of A, then the image of delta r is essentially delta r itself. just a shift horizontally, it doesn't change anything. So this is approximately the same as delta r. There's a vertical twiddling of order 1 over r, but it doesn't matter for what we want to do. Okay, and then the event that you touch this before this and you avoid A is exactly the event that you touch delta r before you touch either r or A. So it just means that you touch delta r before you touch the yellow stuff here. And so if you map it here, what you get is that you touch the image of delta r. So that's the probability that you touch psi A of delta r before you touch the image of the yellow stuff, which is exactly r. That's what you get by psi A. So before r. But now if you remember what I told you the other time, or what Hugo told you in a different way, if you look at the image of Brownian motion by a conformal map, what you get is Brownian motion. So here, this probability is about Brownian motion started at I epsilon psi prime A of 0. So you know that this is Brownian motion. It starts here. You want to hit this line before 0. So this is given by this, except that you don't start at epsilon. You start at epsilon times psi prime of 0. So this is approximately equal to epsilon times psi A prime of 0 divided by r. And there are error terms because this is not exactly here. It's plus or minus 1 over r. These are other terms because psi is not linear here. It's asymptotically linear. But you can check that all the other terms are smaller order than this. So what you get is that the probability that you reach r before 0 and you avoid A is this. So to conclude, now the probability that you avoid A, that K intersect A is empty, given that you reach delta R before delta 0. So it's just the ratio of the probability of the intersection by the probability of the conditioning event. The intersection is what we have here. So that's epsilon psi prime A of 0 divided by r. And you divide by the probability of the conditioning event. This is from I epsilon. This is epsilon over r. So this goes as r goes to infinity and epsilon goes to 0. Just converges to psi prime A of 0. So in the end, what you get is that the excursion of Brownian motion, defined as this limit, satisfies that it avoids A with probability psi A prime of 0 to the power 1. And so what it tells you is that Brownian motion is the restriction measure with exponent 1. The last thing I want to tell you is just some trick that tells you how Brownian motion is related to SLE. Remember this. If you take the union of restriction measures, you just add the exponents. And now we have two particular restriction measures. We have alpha equal to 5/8, which is SLE at thirds, and alpha equal to 1, which is Brownian motion. So if I take 8 copies of this guy, then I get a restriction measure of exponent 5. But restriction measure is characterized by this alpha. And another way of getting the restriction measure with exponent 5 is to take 5 copies of Brownian motion. So what I get is that if I take 8 copies of SLE 8/3, that's the same as taking 5 copies of Brownian motion. This is what we get. So in particular, if you look at the boundary of this, well, this is the boundary of Brownian motion. If you take a point on the boundary of this, it's very unlikely to be on more than one path. And here is the same. If you take a point on the boundary, it's on exactly one of these SLEated. So what it tells you is that the boundary of the Brownian curve looks very much like the SLEated. And in particular, you get that the dimension of the boundary of Brownian motion is equal to 4 thirds. So this was one of the initial motivations of looking at exponents for Brownian motion, to get something about the geometry of the curve. And you will learn a lot about this this afternoon in the exercise session. So I guess now I should really stop for today. The last course is Saturday, and I'm not really sure yet what I will tell you about, but I will figure it out by then. So thank you.